Okay, today we're going to talk about a concept called power. And this is a big concept, so we're going to put our thinking caps on. So, to understand power, we have to understand what confidence level is. Again, one more time. So, confidence level, like when I say I am 95% confident that this interval from this interval captures the true mean or whatever. So my confidence level is the probability that I correctly fail to reject the null. So we want our confidence level to be super high because when it's high, our alpha is low. Remember, 1 minus our confidence level gives us our alpha. So if I'm 95% confident, then I have a 5% alpha. And we remember that alpha is type 1 error, so a super low alpha equals a small type 1 error. This is stuff that we've already talked about before. So we had a clear understanding of type 1 error. We said type 1 error is the mistake that you can make when you take a hypothesis and you decide to reject the null. But what about this type 2 error? What happens when you make the decision that you fail to reject and you're wrong, right? So there's this other concept called the power of the test. So this is the probability that you correctly reject the null. So another thing that people talk about power being is the ability of the test to detect an effect. What does that mean? Well, in terms of medicine, if I'm talking about looking at whether there's a difference between heart medication type A and heart medication type B. And I think the mean difference is 0. And or that's my null hypothesis. And my alternate is that A is actually decreases blood pressure. And I find that in fact, A really does decrease blood pressure significantly so. So I'm going to reject my null. So what I found is data that proved that type A was better than type B, which is an effect, right? So it's the ability of the test to detect that there was an effect, that this wasn't just due to random chance, that something actually was different and that the null is not correct, right? So we really want our power to be high because ideally we want to correctly reject the null. That's what we like to do. So the higher your power, the less your type 2 error. So if we are correctly rejecting the null, we're less likely to fail to make the decision to fail to reject and have it be not true. Now, at this point, your head might be swimming a little bit. I think I had you at confidence level, but power of the test one more time, and then I'll talk about it a little bit more, and then I'll show you some examples. So it's essentially just the probability that you correctly reject the null. So errors were the probability that you made a mistake. Power is the probability that you got it right. Confidence level is the probability that you got it right. Okay, so a little bit more because it's kind of confusing. The power of a test is the probability of avoiding a type 2 error. So it's the probability of finding convincing evidence for the alternate when the alternate is true. That's what power is. So it's the probability of finding convincing evidence for the alternate when the alternate in fact is true. So the way that we're going to calculate power is we're going to say it's 1 minus our type 2 error, and a type 2 error is 1 minus power. So this is the only way that we're going to calculate power. We are not going to calculate it in any way but this. Like you'll get the type 2 error and someone will ask you for the power, or you get the power and you need to get the type 2 error. So it should be pretty straightforward as far as calculations go. But the understanding of it, I think, is a little bit tricky. So let's dive into that. So I've got an applet that I'm going to click on that I think will help you really understand how power works. So we're looking here at a model of kind of how power works. So let me point some things out. We have a distribution here. And oh, look, we have a distribution here. So what's the difference between these two things? This top one is a distribution for what we're testing the null at. So I said that the null was mu equals 0. So let's say our scenario that we're looking at is we want to see, is there a difference in height between seniors and freshmen? So we're going to look at a difference in height, seniors minus freshmen, and we're just going to try to see like, what is this difference here? And we are under the hypothesis that we think, well, a lot of people who are female tend to not grow as much after the age of 14. So maybe we don't see a difference. And then someone else is saying, oh no, yes, they do. We think the mean is going to be a lot higher. We think it's going to be greater than 0. We think seniors are taller than freshmen. So this is our null and this is our alternate for this particular scenario. And we're going to see the standard deviation is about 5 inches. And we're starting with a sample size of 10 and an alpha or significance level of 0.05. Now you're probably wondering, what is this alt mu thing? This was the null that we set forth. We said, hey, the mean is 0. This is a distribution where the mean is, hey, 0. The alternate is like, well, what if this is true? So we're saying, okay, what if we said the mean was 0, but liar, liar, pants on fire, the mean is actually 1. So we're seeing what's the ability to detect or to correctly reject the null if the true mean is 1 when we said it was 0. That's what power is. So what does this picture represent? We know this is at alpha 0.05. So we're looking at, this is the point at which we reject it. This is 95% of the data. This is 5% of the data. So we've made a line here that says over on this side, we're going to fail to reject. And if we have any data that's this extreme or more extreme, we're going to reject the null. So this is the line that sort of marks our decision making, which we define by our alpha. Now this line goes straight down to here. Okay. The only difference is this distribution, the mean is shot over on this side a little bit because this mean up here is 0 and this mean down here is 1. So we're saying, okay, if we make this decision, this line in the sand that says this is where we fail to reject and this is where we reject the null, but this is where the data actually lies, then this red part is our power. It is how often we are going to correctly reject the null. Now, I know that's confusing. Are we ever going to have to do this and map this out? Heck no. I just want to show you the red part represents power. And I wanted to talk to you a little bit about where that math comes from. Are we going to have to do the math? Nope. So as long as you go with me that the red is the power, we're there. Okay, so let's change some things and see what affects alpha. Let's look at this alternate first. Okay, so I told you this is the null. This is the null of there is 0 difference. This one I'm saying there's 1 inch difference. Now let's say that that's actually really small. Let's say there's a small difference. It's just the truth is that it's just half an inch difference. So if I look at that, look, my power goes down. Why does my power go down? Because there's hardly a difference. So it's really hard to detect if I correctly reject the null, it's really hard to have that be true because there is very little difference. Let's say there's the true difference is 2 inches. Okay, now this difference is a little bit greater. Notice this peak went this way, this peak went this way. So I have a lot more power when there's a greater true difference. Let's say the true difference is a whopping 5 inches. Seniors are 5 inches taller than freshmen. Do I think this is true? Absolutely not. But let's look at this for the scenario. Okay, boom. If there really is a height difference of 5 inches and I've said that it's 0, I'm going to easily detect that with my data, right? I'm going to reject that a lot because guess what? In real life, the real mean is going to be over here. So my power is really large. So what I'm saying is, if the truth, which we call the alternate hypothesis, is really different from the null, we're going to have greater power because it's going to be easier for me to see the truth if the truth is really different from the null. Like, it's really going to stand out in the data. Okay, let's reset this. We're going back to a standard deviation of 5. And we'll take this back to an alternate of 1. Okay, so this is where we started before. Now let's look at our alpha. We said this was the line where we were going to reject. And for this one, I'm just going to up the sample size a little bit so we have some high power so you can see this a little bit. Okay, so let's look at the alpha here, 0.05. Let's say I take this down because I'm like, you know what? I want to reject a lot. Notice when my alpha, my error goes up to 20%, that means now I have an 80% confidence level. My power increases. That's just because, honestly, I'm just rejecting more things. Okay. Now, if I take my alpha this way, notice it takes the power down. So if I'm deciding I'm not going to reject a darn thing, I'm going to make my alpha 0.005. Well, guess what? My power goes down because now I'm just not rejecting anything. Like, it's really hard for me to reject. So my power goes down because I'm not going to see when I'm correctly rejecting. Okay, so as I lower my alpha, I lower my power. As I increase my alpha, I increase my power. Okay, which is why we said when a type 1 error goes up, the type 2 error, which is this white section, goes down. So now you can see why mathematically. Okay, I'm going to reset this and let's look at sample size. So going back to our original of what we kind of set forth here. All right, so here's my alpha decision. We're going to keep that at 0.05. And then here is my power. Not very high because I have a sample size of 10. Let's do this. Let's say my sample size goes down to 5. What does that do to my power? Well, it decreases it. Why? Because I have a small sample size. My distribution is not going to be that accurate. Notice that this distribution is pretty darn wide because my sample size is so small. What if I did a sample size of 2? Look, my distribution even gets wider and my power goes down even more. Okay, let's rocket it up to a sample size of 10. Boom. My power goes up. Why does my power go up? Because with a greater sample size, my distribution narrows, right? I have more accurate data when I have a larger sample size. Let's try 50. Now my power goes up even more. Again, because with a larger sample size that shrinks my distribution a bit, I have more power. Okay, what about 100? Look at that. Okay, my power goes up even more. 500. Okay, so with an increase of sample size, I'm just going to have more accurate data. As you notice, this mean is still 0. This mean is still 1, but my distribution narrowed, right? My variability goes down when sample size goes up. So because of that, these distributions got further and further apart, and it's easier for me to, if I reject it, to be correct. And I know that's a lot. So let me, on the next slide, I'm going to write down the summaries of how power changes with the 3 things we just changed. Okay, so to sum up what we just did, increasing power. So how do we increase power? So the power, and I'm going to say based on a random sample size of n and a significance level of alpha, will be larger when. So these are the conditions that increase power. When the sample size n is larger and all other things are held constant, my power goes up. Why? Because my statistics are more accurate. It's more likely that I'm going to correctly reject the null when my sample size is larger. Okay, so the power goes up. The power goes up when the significance level is larger. When my type 2 or when my type 1 error gets bigger, which is what significance level is, my type 1 error gets bigger, guess what? My power gets larger because my type 2 goes down. Remember, we've talked about that type 1 and type 2, if one goes up, the other goes down. So increasing my alpha makes my power go up. If the difference, so the null and alternate parameter values are farther apart. So if there's a bigger difference between the hypothesis, and I said between the hypotheses, like, or hypos is what I actually said. What I mean by that is the difference between the null and what the alternate is, what the actual truth is. If those values are farther apart, it's going to be easier for me to detect a difference. If they're super close together, it's going to be harder. So the farther the alternate is from the null, the higher my power. And then the last one we didn't really talk about, but this is just in general. If my stat is good, if my statistic is good, meaning I accounted for sources of variability, I blocked, I did stratifying, I controlled for other variables, I made sure I did a great, I randomized properly. If I have limited all factors or as many factors as I can that can contribute to this test statistic, if I've designed my study or my survey well, my stat is just going to be better. And because of that, my power is going to be better. So accounting for sources of variability is another key component to increasing the power. Let's try a problem in context. So problem, let's return one last time. We haven't done this before, so we're not actually returning. We're looking at it for the first time. But this problem was talking about a company developing a brand new AAA battery that's supposed to last longer than the regular AAA battery. Based on years of experience, the company's regular AAA batteries last for 30 hours of continuous use on average. The company plans to select an SRS, a simple random sample, of 50 deluxe AAA batteries and use them continuously until they're completely drained. Then it will perform a test at the alpha of 0.05 significance level with the following hypotheses. So our null is 30, our alternate is greater than 30, where mu is the true mean lifetime in hours of the deluxe AAA batteries. The new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer, because if they don't, what's the point of making them? So the power of the test to detect that mu is actually 31 hours instead of 30 is 0.762. Interpret this value. So again, interpret this value means what the heck does 0.762 mean? Okay. So when we're talking about interpreting a value, we need to start with what the alternate is. So they said the power of the test to detect the true mean, or it doesn't say true, but think of it as like the alternate mean, or the mean is really 31 hours. So we're going to be like, well, if the true mean is 31, then there's a 76% chance that the company would find convincing evidence for it being the mean being greater than 30. So if the true mean lifetime of the company's deluxe AAA batteries is mu equals 31 hours. So I'll read that again, so I know it's kind of tiny. If the true mean lifetime of the company's deluxe AAA batteries is mu equals 31 hours, I'm going to pause there for a sec. If the true mean lifetime of the company's deluxe AAA batteries is mu equals 31 hours, then there is a 0.62 probability. Then there is a 0.762 probability that the company will find convincing evidence for the alternate. That the company will find convincing evidence for the alternate of mu is greater than 30. So what are the components to interpreting this? First, I said, if the true mean is the alternate. Then I listed the power. There is at this percent probability. Then I said, in context, the alternate. So I said, the alternate hypotheses. So I said, hey, look, if this true mean is 31, there's a 76% chance that we could find evidence for the alternate, that we could find evidence that the mean is actually greater than 30. So that's what the power means. Hey, if this true thing is 31, when we thought it was 30, there's a 76% chance that we're going to find evidence that that it's greater than 30. Okay, so let's look. The researchers in an Alzheimer's experiment want to test the drug manufacturer's claim that fewer than 10% of patients who take its new drug for treating Alzheimer's disease will experience nausea. That is, they want to carry out a test of the null p equals 0.10 and the alternate p is less than 0.10, where p is the true proportion of patients, like the ones in the study, who experience nausea when taking the new Alzheimer's drugs. Earlier, we mentioned that the power of the test to detect, because that's from a different problem, p equals 0.08 using a random sample of 300 patients and a significance level of alpha equals 0.05 is 0.29. So let me mention those numbers again. It says the power of the test to detect p equals 0.08, that's our alternate, to our null of 0.1. Random sample of 300, and a significance level of 0.05 is 0.29, the 0.29 being our power. Determine whether each of the following changes would increase or decrease the power of the test. Explain your answers. So what we're saying is, how are these things going to change for A if we use an alpha of 0.01 instead of 0.05? If the true proportion is 0.06 instead of 0.08, and if we use 200 instead of 300. So I put at the top of the next page because that's just easier. So let's look at A. What would happen if we use a smaller alpha? If we use an alpha of 0.01 instead of 0.05. Why don't you take a second, turn to your neighbor friend, and figure out what's going to happen. Is, will my power go up? Will my power go down? Okay, let's bring it back. Maybe you were just thinking in your head. Maybe you shared it out loud. I don't know. Okay, so what would happen? Using a smaller significance level makes it harder to reject the null when the alternate is true, because it's harder to reject. So there we go. Okay, B, if the true proportion is p equals 0.06 instead of p equals 0.08. Now remember, it doesn't say this here, but the null was 0.1. So we thought it was 0.1, a 10% difference. Our power was to detect where the true difference is 0.08, and now we're saying, hey, guess what? The true difference is actually 0.06. Talk to your neighbor friend. Does power go up? Does power go down? Okay, let's bring that back. Whether you talked out loud or in your head, we're bringing it back. Okay, so this would increase. So it's easier to detect a bigger difference between the null and the alternate. Like if it's like 0.06 compared to 1 is a bigger difference than 0.08. So because it's a greater difference, it's just going to be easier for me to detect it. So the power goes up. Last one, I'm going to use a sample size of 200 instead of 300. Talk to your neighbor friend. Okay, and let's bring that one back. So this one you should have been quick on this one. Anytime we decrease our sample size, our stat isn't as good, so our power is going to go down. Decreases. A smaller sample size gives less information about the true proportion. Awesome. Okay, so now that we're done with the notes, you had some homework that was due yesterday, but it was a doozy of an assignment. I think there were 3 state plan due or that would be due today. That were 3 state plan due concludes, and I'm giving you some more homework tonight. So I want you to work on the homework that was due today if you didn't finish it, and the homework that is due tomorrow. And then on Wednesday we're going to clear up any questions we have about power because we are taking a quiz on Wednesday. You got this.